Let us now discuss about electrostatic potential and capacitance. In this chapter we are going to discuss about important points on several topics, which are electrostatic potential, potential due to dipole, electric field and potential, potential energy, electrostatics of conductors, capacitors and capacitance, capacitance of a parallel plate capacitor, combination of capacitors, energy stored in a capacitor, followed by practice questions. Now let us understand electrostatic potential. Electrostatic potential is the work done by an external force in bringing a unit positive charge from infinity to a point. That is, it can be viewed as moving a positive charge from infinity to a known point. Electrostatic potential depends only on the initial and final points. It is independent of path taken between initial and final points. Hence, electrostatic potential is conservative in nature because it meets the criterions required for being conservative. Electrostatic potential can be expressed as the fraction of work done per unit charge, that is V equal to W by Q. Electrostatic potential or potential in short due to a point charge is given by V is equal to Q by 4 pi epsilon naught R, where R is the difference between initial and final position of the charge. For a system of charges, that is a system with multiple charges, electrostatic potential is summation of the potential of individual charges. The relevant equations are as mentioned here. Electrostatic potential due to a dipole. A dipole is nothing but a system that contains a positive charge and a negative charge separated by a distance 2a. Here, the potential is given as V is equal to 1 by 4 pi epsilon naught to Q by R1 minus Q by R2. That is, the net potential is nothing but the addition of the potential due to plus Q and the potential due to minus Q. Let us term this as equation 1. From the given diagram, we know that R2 square is equal to R square plus A square plus 2AR cos theta. This is being derived using parallelogram law. Here, on rewriting, we get R square into 1 plus 2a cos theta by R plus A square by R square. If R, that is the distance between the midpoint of the dipole and the point P, is much greater than A, that is half distance between the dipole, then A square by R square can be omitted. Thus, R2 square can be rewritten as R square into 1 plus 2a cos theta by R. Thus, 1 by R2 becomes 1 by R into 1 plus 2a cos theta by R power minus 1 by 2. Using binomial theorem, we get 1 by R2 equal to 1 by R into 1 minus a cos theta by R. Now let us calculate 1 by R1 value. We are following the same approach what we did in case of finding out 1 by R2. Here also we are making use of the parallelogram law. As per that, R1 square is equal to R square into 1 minus 2a cos theta by R plus A square by R square. As mentioned earlier, if R is much greater than A, then A square by R square term can be omitted. Thus, R1 square equal to R square into 1 minus 2a cos theta by R. And using binomial theorem, we get 1 by R1 equal to 1 by R into 1 plus a cos theta by R. Now we know 1 by R1 equal to 1 by R into 1 plus A cos theta by R, and 1 by R2 equal to 1 by R into 1 minus A cos theta by R. Substituting these two values in equation 1, we get V is equal to P cos theta by 4 pi epsilon naught R square. Here P is nothing but the dipole moment, which is given by P equal to Q into 2A. The relevant steps are as mentioned here. Now let us understand the relationship between electric field and potential. The relationship is electric field into distance a positive charge is moved is equal to potential difference. Here, electric field is in the direction in which the potential decreases steeply. Also, magnitude of electric field is equal to change in magnitude of potential per unit displacement normal to the equipotential surface at the point. What is an equipotential surface? Equipotential surface is a surface with constant value of potential at all points on the surface. You need to remember that electric field into distance is equal to potential difference, or electric field equal to potential difference by unit displacement. Let us understand some of the important formulas relevant to potential energy. Now, potential energy of a system of charges, potential energy of a system of two charges Q1 and Q2 is given by U is equal to Q1 Q2 by 4 pi epsilon naught R12, where R12 is nothing but the distance between the two charges Q1 and Q2. Note that U is used to represent potential energy and V is used to represent potential. Now, potential energy of a system of multiple charges Q1, Q2, Q3 up to Qn is equal to 1 by 4 pi epsilon naught Q1, Q2 by R12 plus Q1, Q3 by R13 up to Q1, Qn by R1n. Here, the R1 or the position of the first charge Q1 is taken as the arbitrary point, and all other charges, the distance between all other charges are measured from this arbitrary point. The potential energy of a single charge is Q into V. This can also be expressed in terms of electron volt. 1 electron volt equal to 1.6 into 10 power minus 19 joule. The potential energy of a system of two charges is Q1 into V plus Q2 into V plus Q1 Q2 by 4 by epsilon naught R12. Here, let us say Q1 is the source charge. The potential due to Q1 is Q1 into V. Now, Q2 will experience two types of energies. One is Q2 into V and another one is due to the presence of Q1, which can be represented as Q1 Q2 by 4 pi epsilon naught R12. The potential energy of a dipole, it is given in terms of minus Pe cos theta, where P is nothing but the dipole moment. Now let us understand electrostatics of conductors. Inside a conductor, electrostatic field is 0. At the surface of the charged conductor, electrostatic field must be normal to the surface at every point, that is 90 degree or perpendicular to the surface at every point. In the static situation, the interior of a conductor can have no excess charge. Electrostatic potential is constant throughout the volume of the conductor and has the same on its surface as inside. That is, the electrostatic potential at the surface is equal to the electrostatic potential inside the surface. The electric field at the surface of a charged conductor is E equal to sigma by epsilon naught, where sigma is the surface charge density. The field inside a cavity is always 0. This is also known as electrostatic shielding. Now let us understand polarization. A dielectric develops a net dipole moment in the presence of an external field. This dipole moment per unit volume is called polarization P. Note the equation given here. Here we are using electrical susceptibility of the dielectric medium. The product of electrical susceptibility and external field is nothing but the polarization. Now let us understand capacitors and capacitance. What is a capacitor? Capacitor is nothing but a system of two conductors separated by an insulator. The capacitance is given by C equal to Q by V, where Q is the charge of the capacitor. C or capacitance depends on geometrical configuration and nature of insulator. The insulator is also called as dielectric. It depends on the nature of insulator separating the two conductors. The maximum electric field that a dielectric medium or an insulator withstand without breakdown is called dielectric strength. For a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and electric field do not exceed the breakdown limits. Now let us understand the capacitance of a parallel plate capacitor. The unit of capacitance is Faraday. We know capacitance C is equal to Q by V. Also we know the potential V is equal to E into D, that is the field into distance. Therefore C can also be written as C equal to Q by ED. Now let us calculate the total electric field in a capacitor. Now E total equal to E outside plates 1 and 2 plus E inside plates 1 and 2. The electric field outside the plate 1 and 2 is equal to 0 and electric field inside plate 1 is sigma by 2 epsilon naught, whereas the electric field inside plate 2 is also equal to sigma by 2 epsilon naught. On adding, we get sigma by epsilon naught, which can also be written as Q by A epsilon naught. Substituting this E total equal to Q by A epsilon naught in equation 1, the capacitance can be given as C equal to Q by A epsilon naught into D. Thus, capacitance can also be written as A epsilon naught divided by D, the distance between the capacitors. Now let us understand the effect of dielectric on capacitance. If we assume that the dielectric is vacuum, then C naught can be written as A epsilon naught by D. This C naught refers to the capacitance when the dielectric is vacuum. However, if the dielectric is not vacuum, then C is equal to A epsilon by D, where epsilon is equal to epsilon naught K, which is nothing but the permittivity of the medium. Here K is called dielectric constant and K can be given by C by C naught. Let us remember, for vacuum the dielectric constant K is equal to 1. Now let us understand the combination of capacitors. If the capacitors are arranged in series, the charge Q is constant and the potential V varies. The total potential of the system is given by the summation of individual potentials, that is V equal to V1 plus V2 plus up to Vn. When we write V in terms of C, then it becomes 1 by C equal to 1 by C1 plus 1 by C2 up to 1 by Cn. In case of capacitors in parallel, V is constant and Q varies. Thus, Q is equal to Q1 plus Q2 up to Qn, and the total capacitance or total effective capacitance can be given as simple summation of all the capacitances or all the individual capacitances. Let us understand the energy stored in a capacitor. Energy can be given in different formulas. Energy equal to QE by 2. Energy can also be expressed as Q square by 2C and also as epsilon naught E square by 2AD. And energy density is another term which we need to remember. Energy density is epsilon naught E square by 2. That is the total energy into volume. Now let us get on with practice questions. Question number 1. Two charges 5 into 10 power minus 8 coulomb and 3 into 10 power minus 8 coulomb are located 16 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. The answer is, let C be the point on the line joining the two charges where electric potential is 0. You can refer to the diagram that is given here. Now VCA plus VCB, that is the potential due to charge A and potential due to charge B, when it is added up, it will be 0 at some point between A and B, and let us designate this point as C. Thus VCA is equal to minus VCB. On calculation we get QA by RCA equal to QB by RCB, which means the ratio of charge and distance is constant. Thus 5 into 10 power minus 8 by y. Y is nothing but the distance between A and C. So 5 into 10 power minus 8 divided by y is equal to 3 into 10 power minus 8 divided by 16 minus y. Thus we get y is equal to 10 centimeter from the first charge. That is, C is not exactly at the center of 5 and 3. That is, it is not exactly at the center of charges A and B. However, it is slightly away from the midpoint when we measure from charge A, and it is closer to charge B. However, what if the point C lies outside B? That is, if point C is not between the charges, consider the diagram given here, then again the same formula can be used. On calculation we get y equal to 40 centimeter from the first charge. A test charge Q is moved without acceleration from A to C along the path from A to B and then from B to C in electric field as shown. Calculate the potential difference between A and C and at which point is electric potential more and why. Now let us calculate the potential between A and C. The formula to be used is E is equal to minus dV by dR. That is the derivative of voltage with respect to the distance. This is equal to minus of VC minus VA divided by 2 minus 6. Here 2 is nothing but the x component of point C and 6 is the x component of point A. You could have noticed that we are not considering B for any calculation because the electric potential is conservative in nature and it depends only on the endpoints, not on the path it takes. Thus we get E is equal to VC minus VA divided by R. On rearranging we get VC minus VA equal to 4E, which means VC is greater than VA. Thus electric field is directed from C to A, that is from higher potential to lower potential. A cube of side B has a charge Q at each of its vertices. Determine the potential and electric field due to this charge array at the center of the cube. As far as electric field is concerned, electric field at the center of the cube is 0. This is by Gauss law. And when we calculate potential, we need to consider all the charges. Since the cube has 8 vertices, there are 8 charges Q. Thus potential equal to 8Q by 4 pi epsilon naught R. R is the distance between the charge and the center of the cube. On calculation we get that 2R is equal to root 3B, that is the diagonal which is formed by joining center of the cube and the vertex of the cube is denoted by R, and this R is nothing but root 3B by 2, that is root 3 into edge length of the cube divided by 2. Remember this formula for examination point of view. Thus potential becomes 16Q by root 3 pi epsilon naught B. Question number 4. A cylindrical capacitor has two coaxial cylinders of length 15 cm and radius 1.5 cm and 1.4 cm respectively. The outer cylinder is earthed and the inner cylinder is given a charge of 3.5 microcoulomb. Determine the capacitance of the system. The capacitance of a cylindrical capacitor is given by C equal to 2 pi epsilon naught L by 2.303 log B by A, where L is the length of the cylinder, B is the outer radius of the cylinder and A the inner radius of the cylinder. On substituting relevant values, we get the capacitance equal to 1.21 into 10 power minus 10 Faraday. Question number 5. Determine the potential of a charge at its own location. That is potential of a charge at the place where it is located, the charge is located. We know potential equal to Q by 4 pi epsilon naught R, and since R is equal to 0, because the charge is at its own location, B is equal to infinity, that is it is not defined. Question number 6. Differentiate between electric field and electric potential in a spherical charged shell. The answer is electric field is discontinuous across the surface of a spherical charged shell. It is 0 inside the shell and sigma by epsilon naught outside the shell. However, electric potential is continuous across the surface and it is equal to Q by 4 pi epsilon naught R at the surface.